All right, so let's get started on lecture 15. Gonna do some general functions here. It's more specifically is polynomial functions. So at the beginning of the semester, we talked about polynomial expressions already, right? So that means we just have the expressions doesn't equal to anything. But now if you take the polynomial expression and you stick with that with an output, then you have a polynomial function. All right, so that is what we're going to focus on. So hopefully at the end of this lecture, you could be able to identify polynomial functions, more specifically the degree of polynomial functions, the leading coefficients of polynomial functions, because it's quite important to determine the leading coefficients. Because from the leading coefficients of polynomial function, you can identify other things such as the end behaviors or how the graph of polynomial functions behave. Identify the zeros of polynomial functions with even and odd multiplicity. We look into that. Sometimes you have the graph of the function cross the x-axis. Sometimes the graph touches the x-axis. It means something, and it will tell you the even or odd multiplicity of the graph of polynomial function. All right, so again, determine the end behaviors of polynomial functions analytically and graphically. Right, so here I'm going to give you again the formula for polynomial functions. So polynomial functions of degree n is a function of the form p sub n of x, right, equal to a sub n times x to the power n plus a sub n minus 1 times x to the power n minus 1. And you do this for multiple terms of 2, a2x squared plus a1x plus a0. So what we did when we talk about polynomial expressions is that you start out with a sub 0. That means you only have one term. This is called monomial. And then you add more terms into your expressions. Right. Now you add a1x. So x to the first power. You have, this is binomial because you have two terms. Then you add a2x squared. Now you have x raised to the second power. This is called trinomial, right? So the more terms you add into your expressions with x different power of x, then you have polynomial expression. All right. And by conventions, we write the expressions of the function, in this case, from the highest power to the lowest power. So here, this is called polynomial functions of degree n because the highest degree is n, or highest power of x is n. But in order to say polynomial functions of degree n, you need to impose the conditions that a sub n has to be different from 0. If a sub n is equal to 0, then the polynomial functions becomes polynomial functions of degree minus 1. You would make that. All right. So the number a sub n minus 1, so on and so forth, a2, a1, a0 is called constant coefficients. So these are the coefficients, the numbers stay in front of the x. Now, a sub n times x to the power n is called the leading term. And a sub n is called leading coefficients. All right, so I give you this kind of terminology in order for you to recognize these terms when you work with an example or problem. You could be able to identify the leading term, the leading coefficients, which going to help you identify the end behavior of the functions. So be aware of this. Now, in your polynomial functions, you have a sub 0, right? So I mentioned this yesterday. A sub 0 is actually multiplied with x, but raised to the 0 power, right? So therefore, it is a sub 0 times 1, or a sub 0 by itself. All right. So for a sub 0 by itself, we call that the constant term. And n in this case, the degree of polynomial functions. The domain of any polynomial function should always be from negative infinity to positive infinity. So all real numbers. From negative infinity to positive infinity, or all real numbers. So similar to what we have done in linear functions and quadratic functions, I want you to be able to distinguish between expressions, equations, and functions. Okay. So we cover polynomial expressions already at the beginning of the semester, where you have a sub n times x to the power n plus a sub n minus 1 times x to the n minus 1, so on and so forth, to a sub a2x squared plus a1x plus a sub 0. So this is called polynomial expression. Now, if you take this and then set this equal to 0, then you have polynomial equations. So a sub n times x to the power n plus a sub n minus 1 times x to the power n minus 1 plus a2x squared plus a1x plus a sub 0 equal to 0. Then you have polynomial equation. Now, if you take the expressions and you set that equal to an output, and you have a polynomial function. So we described that at the beginning of this lecture, right? So this is the polynomial equations right here. Sorry, function. So a sub n times x to the power n plus a sub n minus 1 times x to the n minus 1 plus a2x squared plus a1x plus a0, let's say equal to an output called f of x. And this is the polynomial function. All right, so again, by conventions, the polynomial functions or expressions or equations usually written starting from the highest power down to the lowest power. So let's consider the following example. All right. So I give you this polynomial function of the form 4x to the fourth minus 3x squared plus 9 times x to the 7 plus 5 minus 10x. Can you rewrite this function in the standard form? That means start from the highest power and write it down to the lowest power. Okay. So the standard form of this function is f of x equal to 9 times x to the 7 plus 4 times x to the fourth minus 3x squared minus 10x plus 5. So this function is called polynomial functions of degree 7. Because the highest degree or the highest power in polynomial function is 7. Now, by writing in standard form, it's allowing you to identify a few things here: the leading term, the leading coefficients, of course, the degree of the polynomial functions, and identify the constant term. So in this case, the leading term is 9 times x to the 7. And the leading coefficient is 9, right? The coefficient is the number, is a constant in front of x. And degree is 7 in this case. And the constant term, right? So the constant term is the number by itself, doesn't have any x attached to it. It's going to be 5. Simple, right? Straightforward. Now, similarly, let's do example 2 and 3. Right, so you write the function in standard form. That is starting from the highest power and right down to the lowest power. F of x equal to negative 2 times x to the 5th power plus x cubed minus 5x squared plus 7. Nice. This is the polynomial functions of degree 5. The leading term is negative 2 times x to the power 5. The leading coefficient is negative 2. The degree is 5. And the constant term is 7. But again, I want to point out to you that when you get the leading term and the leading coefficients, is allow you to look at or to predict the end behavior of the graph of the polynomial functions. And the constant term, right? If you notice, this is added to the output, so therefore it's allowing you to do the transformations. So positive 7, that proves the original by 7, moving up by 7 units. So example 3, similar to the last two examples, you have f of x equal to negative 4 times x to the 5th power plus 3x squared plus 12. Right. This is polynomial functions of degree 5 again. The leading term is negative 4 times x to the 5th power. The leading coefficient is negative 4, degree 5, and the constant term in this case is positive 12. So we just go over the polynomial functions, right? So polynomial function, poly means many. You have many terms in the functions where the terms have x with different power. Okay. So in practice, when you look at this function, for example, in example 3, you have negative 4 times x to the 5th power plus 3x squared plus 12. So what is the behavior of this function of the graph of the function? It behaves like the function or the x to the 5th power function, because x to the 5th power is called the dominant term. Okay. And then in practice, a lot of time you can ignore x squared and then plus two. When you compare this function or the graph of this function with the function x to the fifth power, it's looking more or less the same. Okay. And now when you do that, that means you drop 3x squared plus 12 here. You only have, let's say, negative 4 times x to the fifth power. When you only have that, negative 4 times x to the fifth power, you call that the power function. Okay. And the power function is extremely important because it's help you use the power functions, and then you can predict more complicated functions such as this one. Okay. So that's the next topic that I want to cover, that power function. And for this power function and or polynomial function in general, it's very important when finding something called the derivative of the function, which again, you're gonna learn that in calculus 1, but the idea is based on this concept that we're learning right now. So a power function of degree n is a monomial function of the term of the form f of x equal to k times x to the power n. Monomial because you only have one term in your function. You with me on that? Polynomial means many terms. Cool. All right, so monomial, just one term. Here you have k to be coefficients. And k and n are real numbers. All right, so I'm gonna give you several example on power functions. So bear with me here. Okay. So when you have a function of f of x equal to 1, it can be f of x equal to 2, f of x equal to 5, or something like that. Doesn't matter. This one is called the constant function. Why is that a power function? Because 1 times x to the power 0. Therefore, it's monomial. It's the power function of degree 0. You may have the function of the form 2x. This is a linear functions, but is in general, this is called the power function because you have x raised to the first power. And this is only one term in the functions 2x. So this is the power functions of degree 1. You have f of x equal to, let's say, 3x squared. So this is called the quadratic functions. This is also a power function. Again, x the second power, but there is only one term in the function. So this is a power function of degree 2. So you may do, okay, f of x equal to 4 times x cubed. This is a cubic function. Or the power function of degree 3. You may have the function of the form f of x equal to 1 over x. This is lecture 11 when you learn about library of functions. Okay, so this is called the reciprocal function. That's the very specific name for that. But you can turn this into x to the negative 1. Okay. And when you write like this is a power function of degree -1, n equal to -1. So reciprocal. You can have f of x equal to square root of x. So you can turn this into x to the power 1/2, and this is square root functions. And this is also the power function because x is raised to the power 1/2, and remember x to the power n for n is any real number. So x to the power 1 is also a power function. So in calculus 1, you're going to see a lot of these functions. Okay, good. And because of that, it would be nice for you to understand that or learn how to turn 1/x into x to the -1, or 1/x squared, turn that into x to the power -2, or you turn this 1/2, sorry, square root of x to the power 1/2, or cube root of x to x to the power 1/3. You would understand that. Okay, because you need those techniques for calculation. All right, so I give you the two graphs here. On the left is a graph of some power functions with even power. So you have x squared, x to the 4th, x to the 6th power. You have different color here. You cannot see that on your notes, but when you look at this graph, you see different colors, and therefore they behave different. So you look at the coefficients, they all positive one or positive number for that matter. That means the end behavior of the functions pointing up in the positive directions. If you have a negative in front of this power function, everything will point down to negative directions. Okay. So on the right here, the graph is for power functions with the odd power. So one side is going to negative infinity, the other side is going to positive infinity, because you have a positive coefficients, positive leading coefficients. Now, if you have a negative leading coefficients, this will change. Switch, okay, between positive and negative coefficients. Now, for even functions, so all power functions of even power, you can see the function is symmetrical with respect to the y-axis, because these are the even functions. Here you have the function is symmetrical with respect to the of the origin, function. So for even, n is even, you have even functions, so symmetry with respect to the y-axis. When n is odd, the function is odd functions, therefore the graph of the function is symmetrical with respect to the origins. So power functions, very similar to polynomial function. The domain is from negative infinity to positive infinity, always, right? Unless there's some very specific case that they clearly mention that the domain is not positive infinity. In general, most of the time, when you consider the domain of polynomial function or power function, they start from negative infinity to positive infinity. So for increasing and decreasing, right? Now, increasing and interval of increasing, interval of decreasing, it depends on the coefficient, on the leading coefficients. In the case of A is positive, right, which you see in the graph, in the first graph, the increasing part is from 0 to positive infinity. When a is less than 0, you have this function look like this. Write it down, so the increasing part of the function is from negative infinity to 0. Now, for odd functions with the positive leading coefficients, increasing from negative infinity to positive infinity, so the function is always increasing. So when a is positive, negative infinity to positive infinity. Now, when you have a negative leading coefficients, the function will always be decreasing function. So I'm going to cover that in the next row. That for odd functions, when the leading coefficient is negative, from negative infinity to positive infinity. All right. Now for the interval of decreasing, when for even functions, when a is positive, the decreasing part is from negative infinity to 0. And when a is less than 0, you have the interval of decreasing is from 0 to positive. All right, so it's a little bit of information here that you need to know. Right? The easy part is to understand or to kind of understand how we get the graph. Right? So the even, when you raise the hand up in football, the graph put the hand up like this, so they even. Okay, even up, even down. From that, you can identify the interval of increasing or decreasing. Now for odd, the odd functions, odd power is always increasing or always decreasing. Good? Yes, no, maybe. Awesome. All right, the next part is finding the zeros of polynomial functions. We're not gonna do algebraic method on finding the zero. I'm just going to look at a lot of graphs on this. All right. So we wrote down the definitions of the zeros of linear functions already, zero of quadratic function yesterday. But here, let's cover that one more time. Okay, so if f of x is a function and r is a real number, for which f of r is equal to 0, then r is a 0 of f. So not only they have a name the 0, there's all the names as well. R is the real root of the functions of the equations. R is an intercept or the solutions of the equations. So there's all the names. R is a real root. Of the equations f of x equal to 0. R is a real solution of the equations f of x equal to 0. Right? So real root View solutions. Or RSA, x-intercept of the graph. Of f. And the next one, we didn't cover that in linear function or quadratic function, but we did talk about this when we talked about the zero of the function, is that x minus r is a factor of f of x. All right. Turning point, we already covered turning point. Hopefully at this point you're familiar with this concept, but we're going to write out the definitions one more time. So the turning point is the point at which the function changes from increasing to decreasing or from decreasing to increasing. Okay, so turning point. A turning point is a point at which the function changes from increasing to decreasing or from decreasing to increasing. So the arrow just to indicate increasing. All right, so before I write down the next two bullet points, I want you to look at this four graphs and tell me something here. So this four graphs are the graphs of some cubic function. Okay, so can you look at this and tell me on the first graph how many turning points do we have? Two turning points. What about this one? Two turning points. What about this two? How many turning points do we have? No. So there's no turning points for those two graphs. Because this is always increasing, this is always decreasing. So there's no change in increasing or decreasing. So therefore, for the last two graphs, you don't have any turning points. Okay. So this is cubic functions. All of this graphs that represent cubic functions. So the most number of turning point we have for cubic function is 2. The most turning point that we can have for a quadratic function is how many? Quadratic function, we learned that yesterday. Quadratic function is parabola. How many turning point that we have for quadratic function? 1. So depends on the degree of the polynomial functions. The most turning point that we can have for polynomial functions of degree n is n minus 1. You're okay with that? Okay. Now, if you have polynomial functions of degree 4, the most turning point that you can have is 3. Okay. Polynomial function of degree 12, whatever that is. Right. You don't know the shape. You don't care about the formula. You just know that the maximum number of turning point that you can have is Okay, it can be 11, it can be 10, so on. Okay. So the second bullet say that if f is a polynomial function of degree n, then f has at most n minus 1 turning points. So let me indicate here, indicate a few things here for this graph. So all of this are cubic functions. You can have here you have two turning points. Here also you have two turning points. Here you have no turning point. So again, for this four graphs, yeah, these are cubic functions. Okay. How many solutions or how many zeros or how many x-intercept or how many roots that we see from this program? So for the first graph, how many solutions? 3. Right, so it cross or touch the axis 3 times. So therefore, there are 3 solutions. So here 1, 2, and 3. So 3 solutions. So cubic function is again the polynomial functions of degree 3. 3 solutions in this case. What about the second graph? How many solutions that we see? 1 solution. And then the last, so this is 1 solution. The last 2 is also have 1 solution. But in general, if f is polynomial functions of degree n, then f has at most n solution. Then f has at most n solutions. All right. So similar to this, when we considered a quadratic function yesterday, right? when you solve for the solution, you use the quadratic formula. Remember yesterday that we talked about that. There are three possibilities, right? You have two distinct solutions, two real distinct solutions. You have one solution or you have no solution. Right, so quadratic function is polynomial function of degree 2. You have at most one turning point and at most two solutions. You're with me on that? Now, if I give you a polynomial, let's go crazy on this one, polynomial function of degree 20, like that. Okay. You don't know the shape, you don't know the formula, but you can tell me this much, that at most you can have 19 turning points and at most 20 solutions. Good. The next concept is multiplicity. Now we try to learn the behavior of the graph of the functions. So the multiplicity is the number of times a given factor appears in the factor form of an equation of the functions. Polynomial of the polynomial function. There are two types. Doesn't make a lot of sense with that definition, but we get into the formula a little bit later and hopefully it make a little more sense. So there are only two types of multiplicity, even multiplicity and odd multiplicity. Okay. When you have even multiplicity, that means the curve or the graph of the functions touches, right, the x-axis at the point. So this is the even multiplicity. The odd multiplicity here is the graph crosses the x-axis. You with me on that? So just two cases, even multiplicity and odd multiplicity. So here, so this is the parabola. This is the polynomial functions of degree 2. You with me on that? And there's only one solution because the graph touches the x-axis. It's only one point. This is the solution. This is the x-intercept. Okay. Even multiplicity. So x plus 3 square. So square indicate even multiplicity. So -3 for x plus 3. -3 here is a 0 solution with even multiplicity. So this point right here is -3, 0. And -3 is a 0 with even multiplicity. On the second graph, you have the graph of the function crosses the x-axis at a point. This one again is the solution or root or the x-intercept, right? And because the graph of the function crosses the x-axis at this point, so therefore we call this is the odd multiplicity. In this case, class 2. It's an odd multiplicity. So 2 is a 0. With odd multiplicity. So now you go back to the two bullets that we have. So if R is a solutions or a root or the x-intercept, Right. So R, let's say solution R is a zero of even multiplicity. So when you have this, this means that the graph of the functions f touches the x-axis at R. Now the solutions R is a zero of odd multiplicity. Then you know that the graph of f crosses the x-axis at R. You good? Good, 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 good. All right. Now, the next thing to cover is the end behaviors. You already see the end behavior earlier here. Right. So the end behavior is the behavior of the function at the end. Right. So the end behavior of this power function is that the function is go to positive infinity when x go to negative infinity, go to positive infinity when x go to positive infinity. Okay. And here, actually, similar to this, when you have something like this graph, the function go to negative infinity when x go to negative infinity. The function go to positive infinity when x go to positive. Okay. So that's the end behavior. The end behavior is that. Can you tell me the output of the function as x go to negative infinity positive? Good. So the end behavior of a polynomial functions go to either negative infinity or positive infinity. And the end behavior of a polynomial function is determined by the leading term of the functions. Now, similar to what you see for the power functions for polynomial functions, behave very similar to what you see in power functions. They're only so when n the degree is even or degree is odd, hence, and when you have the leading coefficients to be positive or negative. So the first row is when you have a positive leading coefficients. And the bottom row is where you have the leading coefficients. So in this case, a sub n is greater than 0. This is when a sub n is less than 0. All right, so this is the notations that we usually use to describe the end behavior. That is f of x go to positive infinity as x go to negative infinity. We use a different color here. And in this case, f of x go to positive infinity as x go to positive infinity. So it's a lot easier to describe the end behavior using graphs. When you look at the graph and you can just tell the output or the end behavior of the function. So here f of x go to negative infinity as x go to negative infinity. And here f of x go to negative infinity as x go to positive infinity. For the odd functions, you have f of x go to negative infinity as x go to negative infinity, and f of x go to positive infinity as x go to positive infinity. Now you switch off when you have a negative leading coefficients. So f of x go to positive infinity as x go to negative infinity, and f of x go to negative infinity as x go to positive infinity. Any questions? All right, so that the end behavior of polynomial functions is very similar to the end behavior of power functions. So I explained a little bit about that already, because for polynomial function, the graph of the function behaves like the leading term. So that's why to identify the end behavior of polynomial functions, usually it can be defined using the leading term of the function. So therefore, it looks very similar to our function. All right, so we have two more examples. So in this example, you have a polynomial functions in a factor form already. So with these functions, let me go back to the definitions earlier that we wrote down that I mentioned. This doesn't make any sense. So the number of times a given factor appears in the factor form of equation of the function. So when you go back to example 5, so let me write example 5 on the board. F of x is equal to negative of x plus 7 to the 6th power times x plus 5 to the 4th times x minus 5 to the 3rd power times x minus 7 to the 3rd power. Okay, so again, the definitions of multiplicity is the number of times a given factor appear in the factor form of the equations of a function. So this is a function. This is a factor form. Why is the factor form? Because it's written as a product of factor. Okay. This is one factor, x plus 7, another factor, x plus 5, factor x minus 5, and factor x minus 7. All right. So this is the factor form of polynomial function. You okay with that? Okay. Now for each factor here, how many factors do you see? 4 different factors. Okay. So x plus 7, how many times is appear in the factor form? How many times x plus 7 appear? 6 times, right? Now for x plus 5, how many times it appear? 4 times. Okay. This is 3 times. This is 3 times. Okay. You good? You good with the definition? I understand. I'm aware that this might sound if you just not right. But hopefully this example demonstrate that concept, that the number of the multiplicity is the number of times a given factor appear in the factor form of the polynomial functions. Okay. So determine first questions here, determine the 0 and the corresponding multiplicity. Okay. How many zeros do you have for this function? Remember, 0 can carry other names as well. Solutions, roots, x-intercept, and x minus r factor of the function. So how many 0 do you see here? How many factors do you see? 4. You agree with me? You're good with that. So 4 factors, that means there are 4 solutions. You okay? 4 of those solutions mean there are 4 zeros, 4 root, 4 x-intercepts. Cool? All right. So there are 4 zeros. That means when you set this equal to 0, you can solve the solutions of x, right? You can solve for x. So the zeros are -7, -5, +5, and +7. That's you. You good? You understand where's all of this coming from? Right. Good? All right. So what is the multiplicity of each 0? What about the -7 here? What is the multiplicity of this -7? Even, so even right here, 6, multiplicity 6. Good? What about this -5? What is the multiplicity? Multiplicity 4. Okay. All right, so this 5, you have multiplicity 3. And this 7, you have multiplicity 3 as well. All right, so again, how to get -7, -5, +5, and +7? Again, you look at the factor, right? And you solve for the factor. So x plus 7 equal to 0. This implies you have x equal to -7. So that's the first 0 that we see here, -7. Now you do x plus 5 equal to 0. You solve for x, you get x equal to -5. Then you have x minus 5 equal to 0, then x equal to 5, x minus 7 equal to 0, then you have x equal to positive 7. And again, the factor x plus 7 appears 6 times, so the 0 is multiplicity 6. So this is 0 of multiplicity 6. This is multiplicity 4. This is multiplicity 3. And x equal to 7 is a 0 of multiplicity 3 as well. All right, so that's just part 1 of the example. You follow? Any questions here? Any questions? Now let's move on to part 2. How do you determine the degree of polynomial functions? So this analysis helps us determine the degree of polynomial. So it's just basically add all of these two together and have the degree of polynomial. Okay. So let me use different color here. So 6, 4, 3, and 3. So from here, degree of polynomial function is equal to 6 plus 4 plus 3 plus 3 is equal to 16. Good. Now you look at, so that part 2, part 3 to choose the end behavior of the graph of polynomial function. So this is the multiple choice question. So it's A, B, C, or D. So remember, the end behavior is determined by the leading term. Okay. So the leading term, including the coefficients and degree of the polynomial. So this is the even degree. So you can ignore A and B. This A and B just for odd function. Okay. C and D are for even functions. Now you have even degree polynomial functions. So C and D, or sorry, C or D. Now that's just degree. You need to take into account the leading coefficients. So this, in this case, is -1. Negative leading coefficient in even power or even degree. The answer should be C. Okay, so here you have even degree. N equal to 16 in this case, and negative leading coefficients. So negative because of this -1 right here. So for example 6, let's consider the following polynomial functions. So the function is of the form x plus 6 times x plus 3 to the 4th power times x minus 3 to the 3rd power times x minus 6. Again, this is polynomial functions that is in fact a form of the polynomial function. So the function is written in this way so that it's easier for us to identify the number of factors that we have Therefore, you can solve the solutions or the zero of the functions. Okay, so there are four factors in this polynomial functions, that is x plus 6, x plus 3, x minus 3, and x minus 6. So for each factor, I'm going to set that equal to 0 to solve for the value of x. Those are the zeros of the function. So x plus 6 equal to 0 implies that x equal to negative 6. X plus 3 equal to 0 implies that x equal to negative 3. X minus 3 equal to 0, implying that x equal to 3. And when x minus 6 equal to 0, you get x equal to 6. So four factors, again, implies that you have four different zeros. And depends on the power of each factor, you can determine the multiplicity of the zero. So the factor x minus 6 appear one time or raised to the first power. So therefore is of multiplicity 1. So this is multiplicity 1. Now x plus 3, the factor appear 4 times or raised to the fourth power. Therefore x equal to negative 3 is multiplicity 4. X minus 3 is a factor that raised to the third power, or the factor appear 3 times, or the zero x equal to 3 is the multiplicity 3. And x minus 6 is a factor that is raised to the first power. So x equal to 6 is the multiplicity 1. So this is just part 1 where you determine the zero and the corresponding multiplicity. So here, after you identify the multiplicity of the zero, you can add all the multiplicity together and you arrive at the degree of the polynomial. So in this case, you have 1 added with 4, and then 3 and added with 1 again. So here, the degree of the polynomial functions, so degree of polynomial functions is that of 1 plus 4 plus 3 plus 1. And this is equal to 9. So this is an odd degree polynomial function. So when you choose the end behavior of the graph of the function, you can ignore C and D because C and D are the graphs of even functions or polynomial functions of even degree. Okay, so the choice is either A or B. Now, to get A or B, you should look at the degree of polynomial functions. Of course, 9 is an odd number. Also, you look at the leading coefficients of the polynomial functions. So in this case, you have positive 1. So it doesn't have any number in front of x plus 6. But it's tell you that is the whole factor form multiplied with 1, which is positive number. So positive leading coefficients with the odd degree polynomial functions. Therefore, the choice is going to be B. All right, so that's it for lecture 15. Please let me know if you have any questions. Thank you.